you ever wondered how it's possible for your computer to run multiple programs at once? From browsing the web to editing documents or watching your favorite TV shows, it's something we often take for granted. But behind the scenes, there's some fascinating computing mechanisms at play, making all of this possible. Today we're diving into one of the unsung heroes of computing, memory paging. This ingenious technique allows our computers to efficiently manage memory, enabling the multitasking capabilities we rely on every day. Not only that, paging also allows a computer to use more memory than is physically available on the system. But for the beginning of this story, we're gonna have to travel back in time.
If only there were a way to run two programs at once!
Leave It to Laurie. Starring Laurie Wired. The Atlas supercomputer from the University of Manchester. And let's not forget, man's best friend.
Back in the early 1960s, computers faced a major hurdle: memory addressing. In this era of computing, memory was a finite and precious resource, often using magnetic cores through which wires were threaded to store data. Each program had to know exactly where to store and retrieve its data from. Not only was this rigid and cumbersome to use, but if you weren't careful, you could easily overwrite the memory space of another program. Let's head back over to future Laurie and take a look at an example. To demonstrate multiple programs being responsible for sharing the same physical address space, I've created this Python script that's going to run two virtual programs that are simply going to print an image to the screen. Now, inside of this program, we have this physical memory array that represents our actual physical memory available to each process. Now, each process is going to be responsible for writing to and reading from the correct area of this array without affecting the other program that's also executing. And you can see our physical memory is a fixed size, just like it is in the real world. Now, if we scroll down, we can see we have two different programs we're going to try to execute simultaneously, Program A and Program B, and both are responsible each for writing to the exact location that is allocated to this particular process. So let's execute that and see what this looks like. Let's go over to our console and let's execute our program. So I'm going to do Python no virtual memory, since we do not have virtual memory for this specific process. Execute that. We have our program A executing just fine. We're printing out our image to the screen. We have the beautiful Mona Lisa look. But let's execute program B and see what happens. Loading. Remember, they're using the same physical address space available to both programs. And it looks like we have program B overwriting the portion of program A in the second half of it. That means that even though the developer tried to start program B in a completely separate area, program B took too much physical space and ended up overwriting the second half of program A, and then you end up getting this whole mess here. Here I've created a visual representation of what memory allocation is like without virtual memory. Program A's memory is symbolized by these blue blocks, and Program B's memory is symbolized by these red blocks. This white tray illustrates our currently empty physical memory. Let's say Program A is ready to start and is about to get loaded into memory. Before we had operating systems to handle it for us, the programs themselves would define their starting addresses. Let's say the person that programmed this decided to start at memory address 0x01. Boom, the memory is mapped to physical memory just fine, and the program proceeds as normal. But now, Program B wants to come in, and Program B was defined expecting a contiguous block of memory, and as you can see, these two blocks are physically connected together. Even though we technically have the physical memory available to hold Program B without overlap, we don't have two contiguous blocks of memory because the programmers didn't collaborate with each other to ensure non-overlapping space. Hopefully this illustrates the major problem with programs physically addressing memory back in the early era of computing. Not only did you have to completely manage memory yourself, but if you wanted to be efficient, you would have to coordinate with all other programs potentially running on the system. That way you could make sure that your starting and ending memory addresses weren't overlapping or overwriting other people's memory. Not exactly feasible, I would say. This is why so often only single programs were run at a time, even if the program only used a fraction of the capacity of the actual machine from a memory standpoint. Even if you have enough memory to theoretically run another program, you can't because of the split memory. So, how do we solve this? Enter the Atlas. Developed at the University of Manchester in the early 1960s, the Atlas was a pioneer in the realm of computer science and one of the world's first supercomputers. It was so large that when Atlas went offline, it was said half of the United Kingdom's computer capacity was lost. But the Atlas wasn't just a powerhouse of a machine, it was a giant leap in computing. Some have even called it the most significant breakthrough in the history of operating systems. What is this breakthrough, you might ask? The Atlas was the first computer with virtual memory. Welcome back to 1962. In the Atlas computer, each program is able to operate as if it has access to a large and contiguous block of memory. These addresses used by the programs are called virtual addresses. The real addresses in computers' RAM, where the data is actually stored, are called physical addresses. Memory is divided into fixed-sized blocks called pages. The Atlas computer uses a special hardware component, an early MMU, or Memory Management Unit, to translate these addresses from virtual addresses into physical addresses. The program is none the wiser, but behind the scenes, there's something very interesting happening. Consider this example from Future Lori. Let's look at an example Python script to represent the advent of virtual memory. Now, with virtual memory, each process has its own dedicated virtual address space, or it thinks it has an entire address space available just to itself. So it doesn't have to worry about stepping on the toes of any other currently executing process. Even though each process has its dedicated virtual memory array, it's still being stored inside of physical memory at the end of the day. It's basically just completely unaware of this fact. Keep in mind, we still have the same amount of physical memory that's available to us on the system itself. However, the advent of virtual memory opens up a lot of different mapping possibilities that we're going to get into shortly. Now, if we take a look at the programs executing, they only have to deal with their virtual address space, and they don't have to be responsible for making sure that they're writing to the correct location inside of physical memory. Now let's take a look at our example running and see if we can print out those images without stepping on the toes of the other program. Let's execute our virtual memory program. Now we have our Mona Lisa printing out to the screen just fine. Program A looks like it's executing successfully. Let's execute program B. Here we go, looking good. Hopefully we don't overwrite the memory. Looks good. And now each program had its dedicated virtual address space, so it didn't have to be aware that any other program on the system was executing simultaneously. Now we'll take a look at a physical example of what's going on. As you can see, I have some additional trays here representing the virtual memory space of programs A and B. The neat part about these trays is that because they are virtual, each program can assume it has a contiguous and consistent address space. So now we don't have to worry about stepping on each other's toes anymore. Program A's virtual memory pages are represented by these transparent blue blocks, which map over to the solid blue blocks of physical memory. Let's pretend for today that each of these pages is, say, 4 kilobyte chunks of memory. Program B's virtual memory page is represented by these transparent red blocks, which map to these solid red blocks of physical memory. In the center, we have a special hardware component called an MMU, or Memory Management Unit. The hardware device is going to translate the virtual memory addresses we're allocating inside of our program into physical addresses in physical memory. You might be wondering what this special orange block is over here. The record of where each virtual page is placed in system memory has to be stored somewhere. The operating system usually keeps a per-process data structure known as a page table. The job of the page table is to store the address translations for each of the virtual pages, thus letting us know where in physical memory each page resides. Phew. That sounds like a lot, but let's walk through how a program allocates memory. Program A requests some space, let's say at virtual address 0x00. It gets allocated a virtual page at 0x00. The OS then instructs the MMU to allocate some space in physical memory, represented by these solid blue blocks, at arbitrary physical addresses. The entry or lookup table of this translation is then stored in the page table data structure in this orange block. When program A needs to, say, load a value from memory into a CPU register, it loads it from the virtual address space. However, behind the scenes, the OS is instructing the MMU to perform a full lookup process, reading the page table, translating the physical address, and then handing the CPU back the correct physical address. This is, unfortunately, very slow. If I'm a CPU, and I'm the MMU, I might have to wait hundreds or even thousands of clock cycles for the MMU to get its act together and come up with the correct address translation. Actually, the engineers at the University of Manchester also realized this problem when constructing the Atlas supercomputer. They came up with an early version of what we would now call the Translation Lookaside Buffer, or TLB for short. The TLB is kind of like a cheat sheet, a small, fast memory cache that stores the most frequently accessed page table entries. Instead of searching through the entire page table, the system first checks the TLB for the entry. If the desired entry is there, it can quickly translate the virtual address to a physical address and consequently save a lot of time. But how does the TLB know which lookup entries to store? That's an interesting problem, isn't it? The TLB uses a combination of both spatial and temporal locality to predict what data is likely to be used. Spatial locality refers to the tendency of a program to access data locations that are close to each other in a short period of time. Temporal locality, on the other hand, refers to the tendency of a program to access the same memory locations repeatedly within a short time frame. Consider this example. Spatial locality is like reading a book page by page. When you finish reading one page, you're likely to read the next page because the content you're reading flows naturally from one page to the next. This is similar to how a program accesses memory locations that are physically close to each other. Temporal locality is different. Temporal locality is like frequently referring back to a particular page or section in a book. For example, if you're studying for an exam, you might keep referencing the same important diagram multiple times. This is similar to how a program repeatedly accesses, within a short period of time, the same memory locations. Just like how both of these methods help humans gather and retain information, the same methods help computers access memory more efficiently. But just like how our memory isn't perfect, TLBs aren't perfect either. Once in a while, you might get a question from your teacher that you're super unprepared for. You might have to flip back page by page across the whole book just to find that one fact that you needed. In computer terms, this is what we would refer to as a TLB miss. TLB misses are very inefficient, which is why we try to avoid them as much as possible. It can take hundreds or even thousands of times longer to look up a memory address during a TLB miss. Uh-oh. I think that's future Lori ready to pop in with some code examples. Let's take a look. Let's execute our program to demonstrate over a number of different trials how the average access time is going to greatly increase as we increase the number of pages that we're checking our access to. That means as we increase the number of pages, we're also increasing the number of TLB misses that we're also encountering. So let's go over to our Raspberry Pi. I'm going to run my script, test.sh, which is going to test a lot of different test cases and then output the access times for each different number of pages that we're executing. So here we go, we're testing with 1 page, 2 pages, all the way up to 8,192 pages. And then if we check our data, that's going to say the number of nanoseconds that it took to access all of the elements inside of the array for all of these different number of pages inside of our program. Now let's plot our data so we can clearly see what's happening here. I'm going to run this with Python and let's plot our data coming from our Raspberry Pi. Now you can see we have this huge increase once the number of pages hits 512. That clearly means that we've hit the maximum number of pages that are able to fit inside of our TLB, and you can see the time per access has greatly increased for every single access that we're trying to make inside of this array. Now you can clearly see that the average access time when the number of pages is able to fit inside of the TLB down here is going to be so much lower than the average access time once you start introducing a ton of TLB misses into your environment. As you can see, I've added a special new block here to our analogy inside of the MMU. This block represents the translation Lookaside Buffer cache. Now, instead of the CPU waiting forever to get the correct memory address, most of the time, the TLB already has the correct lookup ready to go with extremely minimal latency. Now with this whole system, we have most of the necessary pieces for a fully functioning paging system. The convenience of programs being able to assume contiguous memory space has now been completed. We no longer have to guess and check starting and ending memory locations. Instead, the OS and MMU handle that for us. As a programmer, I can now just assume that my memory addresses start at, say, 0x00, even though the physical memory address might be something radically different. We can also take full advantage of the entire physical memory space, even if there isn't a single contiguous block large enough for the program. Also, now with the TLB, the downsides of virtual memory address tables have been minimized. We still have to go back to the page table when we encounter a TLB miss, like is about to happen here. Despite this, we have a system that is quite fast with all of the advantages of virtual address tables and minimal latency. It's really no wonder why all modern computing systems, in one form or another, have adopted this kind of system. Now, I did mention that this analogy isn't quite finished. In more complex systems, we often use multi-level page tables to manage memory more efficiently, reducing the overhead of keeping a single large page table. Another approach is the inverted page table, which can further optimize memory usage by keeping one entry per physical page rather than per virtual page. Additionally, paging to disk allows systems to use disk space as an extension of RAM, effectively increasing available memory at the cost of speed, though. Other concepts like real-time operating systems can sometimes guarantee latency and TLB hits, ensuring time-critical applications meet their deadlines by carefully managing memory and processor resources. There are also different interesting algorithms for paging like FIFO, first in, first out, LRU, least recently used, and random. These algorithms determine how pages are replaced in memory, but we'll save the details of those for another video. The Atlas computer was a spearhead for nearly all of these hardware capabilities and computing algorithms. When referring to the Atlas, Per Brinch-Hansen once said, "It is, I believe, the most significant breakthrough in the history of operating systems." In fact, just recently in 2022, the IEEE Foundation awarded a Milestone of Achievement plaque accrediting the Atlas computer with the invention of virtual memory. It stands as a fascinating milestone in the history of computing. It's a bit disheartening that more praise isn't given to the Atlas and its creators. British computing achievements, in fact, like those of the Atlas project, led by Tom Kilburn, are critical to the story of technology, but often get less attention in American computer science curriculums. Amazingly, there's actually an Atlas emulator available today that can run on modern systems. If you'd like to explore and interact with this historic system and gain a hands-on appreciation of how early virtual memory systems worked, I've linked to it in the description of this video. If you want to delve into how memory management works in a modern context, I'd recommend skimming through the Intel x86 paging guide. Be warned though, it's quite technical and a bit rough to get through. I've also linked to the ARM and RISC-V architecture equivalents, which offer detailed insights into their memory management techniques. In any case, I'd like to take a moment to thank the grandparents of computing, those pioneers who laid down the groundwork for the technology that we take for granted today. Maybe next time you're writing your program, you'll think about the fact that your program's comfy virtual address space is actually an illusion, and there's all of this work going on behind the scenes. Thanks for watching, and I hope you found this journey into memory management and the Atlas computer as fascinating as I did. If you enjoy this style of content, don't forget to subscribe, and until next time, Lori Wired out. How did I even do that? Here we go. Gonna make this turn. Oh, I found the break.